Welcome on Eisenberg, the channel that will help you to upgrade your skills on software engineering. So today we're going a small trick we can see in C or C++, even in embedded system, with boolean variable. So did you ever wonder what is the size of a boolean variable in C or C++? Let's see this together. So I'm on my bool.c file, which I created previously. I'm going to zoom it a little bit for you to see better. Okay, great. I'm going to include the stdio.h, which is the header that will help me to output stuff in my screen. So I'm going to create my main point. So, yes, with the full argument, argc and char rgv, great. And I'm going to return 0. Okay, great. What I'm about to do now is to use the function sizeOf, which take an argument, a variable, not a variable, but a type of variable, and that will display the size of this variable in bytes. So let's use the printf function to display the size. So printf with the size of boolean is, and I will display the size of a boolean, and I will use the function like I said before, sizeOf, with the argument bool. Okay, great. I'm going to end it with a semicolon. Did I forget something? Yes, I did not include the std bool library, not library but header, because there is no predefined boolean type in C without including this header. Great. I'm going to output using GCC. I'm going to zoom it a little bit for you to show better. Okay, great. GCC bool.c, and I'm going to, okay, great, no error. I'm going to execute this file. And what you can see is that the size of a boolean is 1, but not 1 bit like we can expect, 1 byte. Why the size of a boolean, which can be true or false or 1 or 0, is 1 byte? Why does this variable take an entire 1 byte to initialize and declare this kind of variable, and not 1 bit only? Mainly because the way CPU interact with the memory. Well, CPU interact with the memory by reading it byte per byte and not bit per bit. That's why when you declare a variable, the smallest variable you can declare can be only in 1 byte. So we're going to see a small trick which is called bit of field or array of bit that can help us to use a predefined type like unsigned int, for example, to declare, for example, 32 boolean variable using only 32 bits. So let's do this together. So let's go back on the bool.c file to see how it works. So what I'm about to do now is to declare an unsigned int variable, that I will name, that will be named just bool, and I'm going to initialize it using the value 0. For people who doesn't know that what happened inside your memory, when you initialize this variable, which is an unsigned int, which is also a 32-bit variable, what's going to happen is that your memory will be created using this stuff. So 1, 2, 3, 4, 5, 6, 7, 8. Great. So because there is 32-bit assigned to this variable on the memory, there will be 32-bit with the value 0 first, because we initialize it to 0 here. So what is the purpose of the technique which is called bit of field? Is that we are going to assign for each value of this binary representation of the unsigned int variable, for each bit we're going to assign a boolean flag. For example, if I want to use 32 boolean flag for my program, what I can do is to assign for each here bit different value 0 or 1 to see my different boolean. So let's say that I want to output the third bit here to be 1. So that means that my third boolean flag of my unsigned int variable, which is 32-bit variable, will be set to 1, like a boolean set to true. So if it's 0, it will be set to false. So we can do this 32 times here because we are assigning a 32-bit variable using the unsigned int bools. So let's see how to do this. First, don't be afraid. I'm going to use logical operator. Some people, some software engineer don't like this because it's kind of hard, and I don't think it's hard. I think people just don't use anymore, so it's kind of hard for them. So what I'm about to do now is to show you with a small example how it works. So let's go. Let's say that I want to have, for example, at the end of the instruction I will create it, the third bit at 1 and the fifth bit at 1 also. So I want this bit to 1 and this bit to 1. That will represent the boolean flag. So what's going to happen is that I'm going to modify this variable, which is an unsigned int, which is also a binary inside the memory. So I'm going to use the OR instruction. So using this with the OR instruction and with the value 4. So why is the value 4? It might be a little bit tricky, but for people who doesn't know that 4 is also 2 to the power of 2, which can be represented in binary by the value 1, 2, 3, 4, 5, 6, 7, 8. So this binary value is the value for in decimal. So what I'm going to do is to use this binary with this bools variable. By using the OR operator with this binary, which is 4, of course, what's going to happen is that at the end of this instruction, the result of bool will be set to this. So this. So we set up the first boolean bit. So now we need to set up the fifth argument here. So to set up this fifth argument, so it's 1, 2, 3, 4, 5, okay, to the power 4, okay. So we have to reuse this instruction, but by modify slightly something here. I'm going to use 16. Why 16? Well, for the same reason as before, because 16 is also 2 to the power of 4, which is 1, 2, 3, 4, 5. So 1, 2, 4, 8, 16. Great. Which is also 16. So this binary representation is equal in decimal to 16. And by using 16 with the OR operator and the bools variable, what's going to happen is that bools now is going to be equal to this value. So we find a way using the OR operator to set up the third and the fifth bit to 1. So we have now two bools declared in a 32-bit variable. And we can do this 32 times using the same instruction. So we've seen with a small example how to do it. Let's see now, I'm going to erase it. Let's see now how to do it with a simple function by using simply the index of the bit we want to set up to 1 or 0 using the same OR instruction. So I'm going to create a void function and I'm going to name it set bool at, and I'm going to use, yes, great. So it returned nothing, so okay. So I'm going to set up two arguments to this function. The first argument is an unsigned int adx, okay, which represent the index that we want to modify in our binary representation of this unsigned int bool variable. So the next step is the second argument, which will be a pointer to the Boole's binary representation. So what's going to happen is, obviously I'm going to check if I overflow with the index value, the value 31. If I overflow, I will only return. Okay, great. It cannot be negative, so I won't check the negative part of this condition. And what I'm about to do now is to use as before the Boole's variable. Now I'm going to differentiate because it's a pointer. I could use this operator like this, but to keep things simple for you, I will simply use the equal. And like before, I'm going to use the same expression. Now, what I'm going to use here is a small trick. You know that if you want to modify the, let's say the third bit in the binary representation here, yes, what you have to do is to use 2 to the power of 2. So if the index here is 2, because we start at 0 obviously, is 2, I don't want to use 2, but I want to use 4, because I will use 2 to the power of 2. Which is the here 0, 1, 2, which is here is the third argument. So I could use the pow function to set up an unsigned int value here to pow with 2 to the power of idx to set up the third bit here, but I won't use this because I have to include the math library, etc. And I don't want it because we only use a 2 to the power of something. So there is a small trick here that use a bit shifting. So don't be afraid, I'm going to explain it right now. So let's say that I want to have, let's keep this example. So great. So now, if I want to have 4, because it's 2 to the power of 2, which is the third bit of my binary representation, what I'm going to use is 1 shifting 1 to 2 value. Why? But because if we take the 1 here, the binary representation of the 1 is just 1, 2, 3, 4, 5, 6, 7, 8. Of course, because it's 32-bit, it might be another 3-byte 0 here. I will use just the small ones. And if one is here, so it's here, it's the value 1. If I use this operator, so left shift, with the value 2, what's going to happen is that the one here, the bit here, will be shifted by 2 value. So now this one will become this, which is 4, which is 2 to the power of 2, which is 4. So we did what we wanted. We use a small trick here to set up the value that will be used with the OR operator. Great. Now we only have to use it to change the binary representation that we want. Great. I won't use a variable. I will use variable to be more clearer. Yes, I will use this. And I, of course, won't use this. So I will use 1, but I will shift 1 by idx, which what we want. And I will set up here. I will declare here. Okay, great. I will end it with a semicolon. Great. So now if we want to change the bit of let's say the 5th index, what we have to do is to use this simple function with these 2 arguments. What's going to happen is that we'll find the value of the binary representation of the 5th index, which is 1 shifted at left by index, which is 2 to the power of 4. And we will use this value here to, with the OR operator, to set up a new bool bit in the binary representation of bools. What we did is that we created a set bool add function that we take two arguments, so the idx here and the bool and the pointer to an unsigned int variable, that we change the binary representation of this pointed variable with the OR operator. So what we're going to do now is to see if I did a mistake using no, so great. What's going to happen now is that we find the way to change the bit of the idx in the binary representation. What we need to do now is to retrieve the value at the idx in this binary representation. And we can't use the bracket operator like we can do using the static array or the dynamic array. So we have to find a way to extract this information from the binary representation of the bools variable. And we will do this using the AND operator, which is the ampersand operator. So don't be afraid, once again, it will be really easy to understand. So I'm going to create a new function. This time, this function will return a bool to check if this bit is to true or to 1 or to 0, which can be true or false. So it's going to return a bool. Yes, I'm going to name it get bool at. And I'm going to use the same argument as the previous function, which are unsigned int idx and unsigned int pointer to unsigned int variable. Great. Okay. I'm going to add the little check that I did before. So idx higher than 31, so it's overflow. I will return false. Why not? Okay, I won't throw any exception because it's not the subject of this video. And then what I'm going to do is to use the AND operator. Stay with me. So, like before, what we did, we created a value that will be used with the OR operator to set up the bit at the index array of the index bools here. So now I'm going to use the same trick. So I'm going to create a new unsigned int value, which will be the one shifted to the left with the indices. And I'm going to use this value with this instruction. So now I'm going to create a new unsigned int variable, which is named answer, ans for example, and I'm going to use the difference bools here, so the pointed unsigned int variable by the value bools, and I'm going to use the ampersand operator, which is simply the AND operator, and I'm going to use the value here. Okay, you might wondering, why am I using this? What the hell am I using this? Well, it's quite simple once again. Let's see a simple example. Let's say that you use in the main function many times the set bool at function. So you will set up a new new flag in the binary representation of the pointer pointed by the bool variable. So what's going to happen is let's say that you have this kind of binary representation pointed by the bool variable 1 2 3 4 5 6 7 1 2 3 4 5 6 7. Okay, I forgot 4 0. I'm going to add. Okay, so let's say that the variable pointed by the pointer bools have this binary representation, which can be for example, many flag for your program. I don't know, it can be status stuff, don't know, many things. Let's say you have this binary representation. What you want to do now, because we cannot use a bracket operator like I said before, we want to use a simple trick to retrieve the value of the bit at the IDX and this. So how to do it? Okay, what I'm gonna, let's say that I want to extract the value of this byte, which is the third, 1, 2, 3. Yes, let's say I want to extract this value. What I'm going to do is to use the AND operator. How to do it? So to do that, I'm going to show you something. 1, 2, 3, 4, 5, 6, 7, 8. Great, I'm going to copy paste this one time. Oop, I did a mistake. Oh, okay, I think I had 1, 0 here. Okay, great. A simple trick. If you set up the value here to 1 and use the AND operator, so for you to be more clearer, I'm going to use this representation. Okay, great. If I use the AND operator, what's going to happen is that the AND operator will compare each bit here with each bit here. So the AND operator will return 1 only if both of the value are 1. So here it's 0 and 0. It will return sorry, okay, it will return 0. Now if this value is 1 and this value is 0, what's going to happen? It will return 0 like before. Now if this value is 1 and this value is 1, like I said before, the AND operator will return 1. And for the rest of the binary representation, it will return 0 also, because it will compare each bit here with each bit here. And each bit here are equal to 0. So it will be equal to 0 here. And the result will be this, which is 2 to the power of 2, which is 4. I show you just right now how the AND operator works. So it lack of something. So it returns the answer ans here, which is an unsigned int variable, which can be, for example, 4. If I set up the value to here to 4, and if the binary the binary pointed by the variable bools was that. So what I need to do now is to compare ans. Okay, I'm going to leave it some room here. Okay, I'm going to compare ans to the value indices. Sorry, to the value here. And if it's equal, I'm going to return true. Otherwise, I'm going to return false. Can you see why it works like this? Well, like I said before, I'm going to use the AND operator to find this binary representation. Well, this binary representation, if I wanted to retrieve the index number 2, I'm going to use this value to retrieve the index number 2, which is 4, which is 2 to the power of 2. And the result is gonna be 2 to the power of 2, which is 4. And I'm going to compare the value, which is also 4, to the result of this instruction, which is 4 if there exists the third bit here to 1. And I'm going to return true if it's equal, otherwise I'm going to return false. Great. I'm going to delete that. I'm going to look if I did some mistake. So I'm going to reuse the GCC. Great, there is no error. So now, what's going to happen? Let's create, I've already created the bools here. Let's use the two functions created previously to set up new boolean bit on the bool's binary representation. So let's use the function set, I'm going to add break line here, set bool at the index, let's say 3. let's say 0, oh, yes, 3, which is our index 2 because we start counting at 0. Don't forget that. And the second argument is the memory of the bools. Great. End it with a semicolon. So right here, if I could print this binary representation of the boole's variable, it would be this. And after this instruction, it would be normally this. Let's see it together if it works. Okay, so I'm going to use only the printf function to show this. So printf, the value of the IDX2 is set to, and I'm going to use decimal and add a break line. Great. And I'm going to use the function getBool at the index 2 of the memory bools. I'm going to edit with a semicolon. So what it should print here, the value of the index 2 is set to 0, obviously because we did nothing for now. But if I reuse this function here, because we set up bool at the index 2, it should be 1. This function getBool at 2 should be 1 because we use the AND, which is an ampersand operator. So let's compile and use this executable. Okay, no error. Hope it works. Great. So you can see that at the first printf function return, the value of the index 2 is set up to 0, which is logical here because we did nothing. But after that, after this instruction, what's happened is that we slightly change the binary representation of this unsigned int boolean variable. So now the value of the IDX2 is set up to 1. If I change, for example, the value, if I reuse this function, let's say I reuse this function, and I want to, let's say the bit number 30. What I'm going to do is to change this argument with 30 and this argument with 30. Let's say if it works, I'm going to add a small break line here to be more clearer. Yeah. Let's simply do this for, okay. Great. I'm going to recompile my file. There is no error. Okay. So you can see that I change also the value, the bit number 30 in my binary representation. So it works perfectly. We can now do this 32 times. And if we use an unsigned rather than an unsigned int variable, if we use a long variable, like in C or C++, we can afford to do this. So we could have 64 bit, and we could set up 64 bools using this variable. You now know how to set up 32 up to 64 bool using only binary representation and the OR and AND operator. If you like this video, please like it and subscribe to my channel if you want to learn more about programming and software engineering in general. Thank you and see you soon.